Okay, let's talk about some specifics now. So up to this point, it's like theoretical. The electrons are going to push each other around. There's electron pair repulsion. What does that actually look like in practice? So let's come back to that one of those molecules we looked at the beginning of the video, of the set of videos, carbon dioxide. So let's think about looking at the carbon. So for all of this, we're going to be looking at the central atom. That's going to be our starting point for everything. And we're going to be starting with molecules that only have a single central atom to keep things simple. But we will build up to things that have more than one central atom or multiple atoms linked together. But for Vesper theory, we're going to start with just one group of atoms at a time, or with one single central atom. Now, for this carbon, let's look at the electron pairs around it. Right? So we're going to ignore the lone pairs on the oxygen. Those are not going to matter for now. We're just thinking about just relative to our carbon right here in the middle. Right? So we have our lone pairs are going to be right here and here. So we have each oxygen bonded, and so there are a total of 4 bonding pairs. If I said lone pairs, I meant electron pairs. But they're grouped into two groups, right? So we could say that there are 2 groups of electrons, right? Even though they're double bonds, it's just a single attachment to an oxygen atom. And those 2 groups of electrons are going to want to be as far apart from each other as possible, as 2 double bonds. So we could imagine, we could do, something like this, where we have a right angle right here. So this angle of 90 degrees between oxygen and carbon, but that puts these electrons closer to each other. And so these, if we imagine, these electrons here staying in place, they're going to push on these other electrons and repel them, and they're going to push them as far away as they can go. And the furthest away they can go is being 180 degrees away. Because if they get pushed any further than that, then the angle gets smaller, right? So the furthest apart if you have 2 groups of things, for them to spread out, they're going to spread out completely on opposite ends. And that ends up with our molecule being in a straight line. So this bond angle that we call it here, which is one of the things we'll be keeping track of to keep track of these geometries, is 180 degrees between our carbon-oxygen double bonds in carbon dioxide. All right, and so we can generalize this. This will be true for anything that has 2 groups of electrons like this. And so what we'll start to keep track of for these different types of molecules we're going to look at is what's called the steric number. This is the term that your book uses. And the steric number is the number of atoms bonded to the central atom plus the number of lone pairs. And what we're doing here is we're keeping track of how many groups of electron pairs do we have around a central atom. So in this case, our steric number was 2, and for any molecule that has a steric number of 2, it will be a linear molecule. So carbon dioxide is only one example, but it won't. But we'll see some examples in the future where you can have 2 atoms bonded to a central atom, just like carbon dioxide, but it's not linear, and that's because those molecules will have lone pairs in them. We'll get there. We're not there yet. Okay, so this is an example of a molecule with a steric number of 2. To spread them out, you're going to push them out 180 degrees apart from each other. That's going to push them out. What if we have 3? So what if there is a molecule like BF3, boron trifluoride? We looked at the Lewis structure of this in the last chapter. So this, we end up with a structure like this, where we have lone pairs around all fluorines, and there are 0 lone pairs on the boron, unless we draw a resonance structure. Well, even if you draw a resonance structure, there's still 0 lone pairs. All right, so this is going to have a steric number of 3. And to spread out those 3 electron groups, so our electron groups are the 3 single bonds here now, what's the best way to do this? Well, if you look at the geometry of it, you can't push them 180 degrees apart because now there's something else in the way, right? So if this one got pushed to 180 degrees, it would be closer to this bond over here. So you can't put 2 of them at 180 degrees. So it ends up the best way to spread out these electrons, so to minimize the repulsions between them, is to put everything in a plane at 120 degrees. So they're sort of spread out a third of a circle apart from each other. Right, and so this is something with a steric number of 3. This will work for all molecules, not just boron trifluoride. All right? We'll go ahead and move up to steric number 4, and that'll be the last we'll get to in this video, but you can go higher, and we will go higher. So what about something like methane? So again, coming back to this example we looked at the beginning of the chapter, something that has 4 bonds to it, no lone pairs. So steric number of 4, but still no lone pairs. So far we're just considering things without lone pairs for the time being. Now, you may think the way I drew it here is going to be the best way to put these where we have these 90-degree angles here. But remember, these are in 3-dimensional space. And so what's actually going to happen is that this will form this tetrahedral geometry. So our carbon will be in the middle. We'll have one hydrogen pointing straight up, and the other hydrogens will be at an angle relative to this. So one will be pointed, in the bond angles here are all about 109.5 degrees. And we have one hydrogen going back away from the carbon at an angle, and one coming forward. And so that's what these dashed lines and wedged lines are to represent, is that one going back, one going forward. Now, let me see if I can find a better picture of this. This is from your textbook. So this is the geometry I'm trying to indicate. So if you imagine all the hydrogens as being these points along the outside of a sphere, this is the best way to spread them out, is to put them inside of this tetrahedral shape. So it's a pyramid that has a triangular base to it. So it's not spread out 120 degrees or 90 degrees, but it's this 109.5 degrees. So this is the shape of a tetrahedron, if you're familiar with that from geometry. Okay, so far, summary, we have our 3 different shapes, and we'll go back and look at all of these, right? So if for steric number of 2, and again, all these examples we're going to look at for this video are no lone pairs. So we have this shape, linear. I'll just pull over this figure as well. Right, so these are completely pointed opposite of each other in 3-dimensional space, so it makes a line. Our BF3, our steric number of 3, where we have 3 bonds around a central atom, is this 120-degree shape. So this is what we call trigonal planar, is the official name of it, meaning it's a triangle that's flat. It's in the shape of a plane. And this is the best way to spread out 3 things that are on the edges of a sphere. And again, the whole point of this is the electron pair repulsion. So the electron pairs in these bonds are pushing on each other and pushing each other away from from each other, but still attached all to that central atom. And then our final one, in this video at least, looking at steric number of 4, is this tetrahedral geometry. So now we're not dealing with things that are in a flat plane anymore, but this is now this tetrahedral pyramid shape that we have for methane.